And good morning. And we're going to be going over some conservation of momentum today. So let's get away with it. Remember that word conservation. Conservation, any of our conservation laws basically tell us two things. They tell us that there's a before and an after. And those two pieces, the before and after, need to be equal to each other. They are always conserved. So depending on what we're talking about, the first one we learned about was conservation of energy, which means that energy is never lost or made up. It's always just passed around, right? It's always conserved. You can always keep track of the before and after. And what we're going to be talking about today, this new one, is conservation of momentum. And conservation of momentum is really handy when we're doing things that have to do with collisions and explosions. And collisions and explosions look a little different, and they're not gonna, like, everybody sees the word explosion and they're like, oh yes, and they picture the Hollywood like massive fireball or anything. Not quite. Okay, the physics definition of those two things is for a collision. A collision is any time two things run into each other, right? So you have, a wall, and there's our wall, and unfortunately you have a sad car, horribly drawn car, but it's flying towards the wall, right? They hit, that's a collision, right? Also, like billiard balls, right? You got one billiard ball that's sitting there at rest. You got this other billiard ball that's flying that way with some velocity, right? And then they hit, boom, and then that other ball stays still and the other ball goes flying away. So that's a collision. Now, different than that, we have something called an explosion. And an explosion is when we have one thing that bursts apart into multiple things. So, for example, you have a skateboard with a person on it. That person's holding a big ball, right? Person throws the ball to the right, which means they had an initial velocity of 0 as some combined system. And at the end, person threw the ball to the right, and now they're going to the left. Okay? That is considered an explosion. One piece became many. And so that's how we're going to kind of describe these things. If we're talking about conservation of momentum, all that means is that the sum of all objects need to equal all momentums or momenta at the end. Okay? So what does that mean? If I want to add up all the momenta at the beginning, that is the sum of all the momentums initially. And then we're going to set that equal to the sum of all momenta at the end. Okay, so that right there is our conservation law. All of the momentum initially needs to equal all of the momentum at the end. We can take this a little step further. We can say the sum, remember the equation we have for momentum is mass times velocity. So we can say the sum of all mass times velocities is going to be equal to the sum of all mass times velocities at the end. Okay, and you'll see what I mean when we're using this in the examples. Okay, so this is our conservation of momentum law being set up. And so let's take a look at these. Here's our first one. A 75-kilogram person is standing still on an ice rink, and they throw a 5-kilogram turtle to the right at 20 meters per second. And that thing on the ice, that is an implication that it is a frictionless surface. And so we're being asked. So this right here would be an explosion, right? We have a person. Actually, it's really similar to that one I just drew. We have a person standing there on ice holding a turtle. There's a turtle, right? And then initially they both have a momentum or a velocity of 0 because they're just standing still, right? When we throw the turtle, now all of a sudden the turtle gets thrown, the turtle's going that way. So the person is going to go in the opposite direction, right? That is an explosion. We have one object to two objects. So when I set this up, let's go ahead and start by saying the sum of all initial momentum is equal to the sum of all final momentums. I know that I'm going to use conservation of momentum because this is an explosion. An explosion or a collision, the best tool I have to answer anything about those things is conservation of momentum. Okay, so what are all of my initial momentums over here? Well, remember mass. There's two objects here, so I'm going to have two momentums. There's the momentum of the turtle plus the momentum of the person. And those are all initial, and then I need to do the, and actually, you know what? The person and the turtle are combined. So we're going to say the momentum of the person and turtle. And that's got to be equal to the momentum of the turtle at the end plus the momentum of the person. Person at the end. Okay? So, momentum is mass times velocity, right? So mass of the person and turtle is going to be equal to the momentum of the turtle at the end plus the momentum of the person. Okay? Now, at the beginning, they're standing still, so the velocity is 0. So this whole thing cancels out and goes to 0. Right? We are being asked to find the final speed of the person. So let's get the speed of the person right here all by itself. That's what we're trying to solve for. So let's isolate that variable. And once we do that, we have all of the things that we know and that we need. Okay, so we could plug in all of our values and get our, what is that, 75 kilograms for the person. So 100 divided by 75 is 1/3. So 1.33. The person is going to have a velocity of, and this is negative 1.33 meters per second. Why does that make sense? Because if the person throws this object to the right to conserve momentum, then something, if it wasn't moving before, now something's moving to the right, something else must be moving to the left to account for that and to balance everything out, to make sure momentum is conserved. So, yeah, we have the velocity of the person is now going to... In this one, they actually stick together. So rather than an explosion happening, now I'm going to have a collision, and they stick together. Okay, so in a railroad yard, a train is being assembled, a empty boxcar coasting at 3 meters per second. So that right there is going to be some type, oh, good Lord, some type of velocity. strikes a loaded car that is stationary, so that's initial velocity for that one, and the cars couple together, so they stick. Each of the box cars has a mass of 9,000 kilograms, and the loaded car contains 55,000 kilograms of lumber. Okay. Remember, I like to draw pictures just to kind of get an idea of what's going on. So we have this box car, and it's coasting to the right at 3 meters per second. Okay, and then it's going to hit this other box car that is just chilling at 0. Okay, and it's full of stuff. So this is 9,000 kilograms, and then this one is 9,000 kilograms plus the 55,000 kilograms of stuff inside of it. So that's what, 64,000 kilograms? Okay. When they hit and stick, now they get stuck together. And we know it's going to be going to the right at some final velocity. We don't know what that final velocity is yet, but we know that when they get stuck together, now the mass of the entire thing is the combination of those two. So it's 9,000 plus 64,000. So what would that be? 73,000 kilograms. Okay? So now we have our picture drawn out. We have a good idea of what's going on. We're being asked to find the speed of the coupled boxcars, so when they get stuck together. So that's what we're going to do. Right? Conservation of momentum. So I need to add all the momenta of the objects in the beginning. So that's the, let's call this boxcar 1. Let's call that boxcar 2. So we have the 2 objects. We call that 1 and 2. Good. So that would be the momentum of 1 plus the momentum of 2, object 2, equals the momentum of 1 and 2 put together. Right? So when we do this now, this would be mass of 1, velocity of 1, plus, we know the momentum of this is 0. So let's just make that 0 right away. Right? So we don't have to worry about it. And then the momentum of this one is the combined masses, mass of 1 plus mass of 2, times the final velocity. And from here now we can actually solve for this. So I would just isolate this variable to get m1 v1 all over this mass. And from there, now I can plug in all the values I know, right? I can plug in, that is 9,000 kilograms times 3 meters per second, all divided by their total mass, which was 73,000 kilograms. So if I do that real quick, that is 0.37 positive 0.37. So when they combine, they move to the right. A lot slower than they did initially, because that makes sense. There's nothing new put into the system, so if it combines and gets heavier, it's going to start moving slower.